Modern AI systems, powered by large language models, function as autonomous workers, executing complex, multi-step tasks like generating code and remediating incidents. But these models share a severe architectural limitation. They are stateless entities. When initialized, an AI agent's entire memory exists inside the context window. Think of it like RAM. It is highly volatile, temporary storage. The moment an active session ends, or that window fills up with data, the agent's memory resets entirely to zero. An agent cannot execute a multi-step workflow if it immediately forgets its previous actions the second a session closes. Statelessness prevents true autonomy. The standard industry workaround for a stateless model is RAG, or Retrieval Augmented Generation. RAG connects the large language model on the left to a vector database on the right, containing historical data. The agent queries this database, pulling relevant context backward into its window before generating a response. However, RAG has a structural flaw. It's a read-only operation. RAG solves the input problem, but ignores the output. If an agent writes a Python script or remediation playbook, where does that work product go? With no return pipeline to storage, the file has nowhere to go. RAG allows an agent to read the library. True autonomy requires persistent read-write agentic storage to actually save its work. The engineering solution is treating the AI agent like a standard application, providing it with a hard drive to persist work between sessions. Look at this animated diagram of an enterprise storage environment. Data is fractured. Here, a single AI agent faces three entirely distinct storage silos: object storage, block storage, and NAS, which stands for network attached storage. Connecting the agent to these silos requires severe engineering friction. Each underlying system demands its own custom API integration. Beyond disparate APIs, these storage systems utilize completely different data models and entirely separate authentication mechanisms. Engineers are left writing and constantly updating bespoke integration code for every single storage interaction. As enterprise environments scale and add more data silos, this one-to-one integration model fails to scale. Hardwiring agents directly to hardware infrastructure creates an entirely unmaintainable system. The architecture requires a universal translation layer. The industry standard converging to solve this is the Model Context Protocol, or MCP. This animated diagram demonstrates the MCP architecture. The top layer is the MCP host. This is the application environment where the AI agent actively runs. At the bottom of the stack is the MCP server, representing the underlying storage layer. These two layers communicate via a unified pipeline using the MCP protocol. This protocol standardizes all data transfer into JSON RPC, a lightweight, text-based remote procedure call format. MCP acts as a universal adapter. It presents a single, uniform interface to the agent, while the server automatically handles routing to the object, block, or NAS silos below. The AI agent no longer needs to possess specific authentication keys or understand the unique data models of the backend hardware. By transforming a chaotic web of custom APIs into a single standardized pipeline, MCP allows AI agents to operate across any enterprise environment at scale. To safely structure these storage interactions, the MCP server exposes its underlying capabilities to the agent through two distinct categories called primitives. In this animated diagram, we see the first primitive, resources. This is the blue pathway branching to the left. Resources are passive data objects like file contents or database records that the agent requests strictly for context, exactly like RAG. The second primitive is tools. This is represented by the downward-flowing red pathway on the right. Tools are executable functions exposed by the server. They allow the agent to issue active commands, such as listing a directory, writing a new file, or creating a storage snapshot. Separating passive read requests from executable actions gives the agent a highly structured, predictable vocabulary to manipulate its environment. Establishing a uniform write pipeline exposes a critical security flaw. Autonomous AI agents hallucinate, and they operate without broad situational awareness. Granting an AI direct write access to enterprise storage is catastrophic when compared to standard human identity and access management, or IAM, which are permission frameworks designed strictly for humans. Agentic storage requires AI-native safety layers built directly into the storage infrastructure itself, entirely superseding whatever permissions the agent thinks it holds. The first safety layer is immutable versioning. An agent sends a write or overwrite command down the tool pathway to a specific file. Instead of replacing the existing file, the storage layer forces a new version to be created. The original file drops into a shielded archive layer, and the new file takes its place above. Under this strict protocol, an AI agent can never truly delete data. It only possesses the capability to archive it. Immutable versioning guarantees a complete mathematical audit trail and instant rollback capability, mitigating the risk of a hallucinated deletion. The second essential safety layer is strict sandboxing. This targets the confused deputy problem. This occurs when an agent with broad permissions is tricked by malicious input into acting outside its designated operational scope. Sandboxing forces the agent to operate within a rigidly constrained directory enclosed in a strict, highlighted perimeter. If scoped solely to manage application logs, its access is physically isolated. Any tool command sent to a system binaries folder shatters against a solid firewall boundary. Sandboxing ensures that even if an agent's internal logic fails completely, the physical blast radius of its actions remains contained within non-critical zones. The third and most advanced safety layer is intent validation. Before high-impact operations, the storage gateway pauses a delete command, demanding a reasoning payload. The agent supplies a logical chain of thought, like citing a 90-day retention policy. The system verifies this claim against business rules. If matched, the gateway turns green and executes. Pulling back, we can now see this animated diagram of the fully realized agentic storage architecture. An MCP host communicating via JSON RPC to an MCP server, passing through three concentric hardware shields of versioning, sandboxing, and validation before ever touching the underlying storage. Agentic storage functions as a specialized AI-aware translation and security protocol, providing the persistence required for long-term task execution. By combining the standardized language of MCP with immutable guardrails, engineers can safely upgrade stateless models into highly autonomous, enterprise-grade digital workers.